Hi, today we're going to do an application of improper integrals, and it has to do with a marginal profit function and using that to find a total profit. So one thing I want to just remind you of is when we take the integral of a rate function, and when I say a rate function, I mean a derivative. What it gives us is it gives us the total accumulation of that function. So when we take the integral or antiderivative of the marginal profit function, which is a rate function, what we're going to get when we do that is we're going to get the total of that function, of the profit. We're going to get the total profit. So for us, what we'll be doing is we'll be taking the integral of the marginal profit function, and then what that's going to give us is our total profit. Now, it might be from A to B, or it might be, from whatever other limits of integration. So it'll give us a total profit, from A to B. Sometimes they call it the net change. Okay, so for us, here's the problem that we need to take a look at. We need to take this marginal profit, and because they're going to make infinitely many units of this item, we're going to need to integrate this from 0 to infinity, this 80 e to the negative 0.033x dx. So when we integrate this function, what we're going to get is we're going to get the total profit for producing infinitely many units. Okay, so that's our goal. So this is called an improper integral because it has a bound that is to infinity. And so it's going to take some little calculus tricks to evaluate this. All right, so here we go. So what we're going to do, because infinity is not really a number that I can find or plug in, we're going to replace infinity here. We're going to do the integral from 0 to b. We'll let infinity be represented by b. So out here, we're going to do the limit as b goes to infinity. So for now, we're going to replace infinity with b and then attack this integral here. All right, so we do our normal antiderivative, and then at the end we'll substitute back our infinity. So if you recall, we have the rule for antiderivatives of functions of the form e to the kx. So we're going to be using this. So we're going to apply that here. So the 80 is just a constant, so that's going to stay the same. So let me keep my limit in front of this as we go. So we keep our 80 here. And then the antiderivative of the e part of this is going to stay e to the negative 0.033x, but divided by negative 0.033. And then we're going to evaluate this from 0 to our value b. Now, dividing 80 by negative 0.033, that does not divide nicely. If you like, we could put the fraction form of that. So if you type that in your calculator, if you type in 80 divided by 0.033 and convert that, to a fraction, you're going to get 80,000 over 33. So I'm going to change it to this, 80,000 over 33. Now that e with this negative exponent here, I'm going to put that on the bottom of my fraction. With a negative exponent, I can put it down on the bottom, and that way I can make the exponent a positive exponent. So there we go. And then we're going to evaluate from 0 to b. Okay, so then we're going to evaluate by plugging in the upper limit b, subtracting, and then plugging in the lower limit 0. So all the time I still have this limit in front. I'm waiting sort of until the end to take care of that. So I've got negative 80,000 over 33 e to the 0.033, and then I'm going to plug in b minus our negative 80,000 over 33 e to the 0.33 times 0, right? So we're doing the f of b minus f of a, that fundamental theorem of calculus. Okay, so we're plugging these in. Now, I can't plug in, say, infinity, so I am going to eventually take and do the limit, and just for this b, we're going to let this b go to infinity. So what's going to happen there is when b becomes a very large number, e to that very large exponent becomes even larger, and then multiplied by 33 is even larger. So what you end up with is this negative 80,000 divided by a very large number. And I mean really, really large. So what happens is essentially it goes to 0. So this part becomes 0. Now then we still have our double negative here, minus a minus. So I'm going to make that a plus. And then we have 80,000 over 33 e. And then that exponent, 0.33 times 0, this is going to be 0. Now e to the 0 is just 1. So now here's what I'm ending up with. I have 0 plus I have 80,000 divided by 33 times 1. So 80,000 divided by 33. So my total profit, and since this is money, I'm going to change this back to a decimal form where I can round it off to 2 decimal places. So if I divide 80,000 by 33, I'm going to get this number here, 24, 24, and 24 cents. So the total profit is this for making infinitely many items. Many units in this case. So there's our application of our indefinite integral. When we want to evaluate something at infinity, this is the process that we have to go through. Thank you. I hope this has been helpful.